Hey guys, so today we're going to do the test number 4 review. As always, you can open up Excel, flip the screen, and then load up the test review. So this test review is this test number 4 is mainly about statistical inference, and really, in other words, making claims about a population, about an unknown population. So this whole idea is we take a sample from a population and we can use the results of that sample to generalize about larger scale things. And what that means is we have to formulate hypotheses. And that's what these first couple questions are about. I'm not going to read this whole paragraph. This is number 1. So the BLS reported, or at least a report in 2015, displaying and detailing unemployment rates by educational attainment people aged 18 or older. Although the trend shows a decline over the last 5 years, the unemployment rate of those with a high school diploma is reported to be higher than those with some college or an associate's degree. And educational researchers from a certain state believe the gap in unemployment is smaller. So this is really all you need in this problem to create your hypothesis. So your null hypothesis is your status quo, your unemployment rate is higher. Your alternative is then what the researcher believes. So they believe that the unemployment rate of those with a high school diploma is going to be smaller. So for that high school diploma, let's see, higher. The unemployment rate of those with no high school, higher. Or smaller. Alright. According to a report published by the Bureau of Labor Statistics in April 2015, women were making 78 cents for every dollar that their male counterparts were making. Some business partners of a large company believe they compensate men and women more equally. They tasked their HR department to provide statistics displaying and comparing mean salaries of men and women. A random sample of 300 men and women observed. Okay, what are the null hypothesis? Well, the null hypothesis is really that they compensate equally. The average salary for 78%, no. The average salary is 78%. The average salary of women is lower than 78% of their male counterparts. So that's what they're saying. We're making 78 cents for every dollar that their counterparts are making. So, 78%. The average size of women is greater than 78. No. And actually, I would say this. The null hypothesis is going to be the average salary is not related to gender. It's equal. What? That's really what it would be. Well, then it would be this. Your null hypothesis, is that null or alternative? I'm sorry. So your null hypothesis is that the average salary for women is 78%, because they make 78 cents for every dollar they make. But the same question, what is the alternative hypothesis? Well, the alternative hypothesis would be that, same question, the data doesn't really matter, but the alternative hypothesis, since this is our null hypothesis, so the average salary for women is greater than 78% of their average male counterparts. Basically saying they make more than 78 cents for every dollar. The following hypotheses are tested. The null hypothesis is the proportion of U.S. adults who support their current president is 49%, and we're saying that the current approval rating is less than 49%. So based on the data collected, the p-value is found to be 0.045. So what can we conclude based on the p-value? So the whole thing you're looking for is, when making these decisions of rejecting the null hypothesis or failing to reject the null hypothesis, is you're going to compare this p-value with your significance level. Now, if the significance level is not stated, it's generally just assumed to be 0.05. So what we're looking for is, if the p-value is lower than this value, we reject the null hypothesis. If it's greater than, we fail to reject. So 0.045 is less than 0.05. So we're going to reject the null hypothesis in favor of the alternative. So when we reject, we say that there is significant evidence, or there is evidence that, we're favoring the null or the alternative. So they had to provide significant evidence that the proportion of U.S. adults who support their current president is 49. No, we rejected this. We rejected the null hypothesis in favor of the alternative of less than. So the data provides significant evidence that the proportion of U.S. adults who support their current president is less than 49%. Same thing. We have a null hypothesis. We have the alternative hypothesis. So we've sampled 2,000 U.S. citizens and a p-value of 0.073. Now, while this number looks small, it is not smaller than our significance level. So we cannot reject the null hypothesis. We failed to reject. So we basically say that there is not significant evidence that the proportion of U.S. citizens who attend college immediately after graduating high school is less than 57.5%. So note that I'm always making this interpretation in terms of my alternative hypothesis. There either is significant evidence for the alternative or there is not significant evidence for the alternative. We're never answering this question in terms of the null. So we fail to reject, so there is not significant evidence to conclude that, that's not it, this one, the data do not provide significant evidence that less than 57.5% of U.S. citizens attend college. Alright. 2012, okay, blah, we have to read this. Really, all we're looking for is, based on the p-value, 0.0078, what can we conclude? Well, whatever our hypotheses are, because our p-value is so low, we're going to reject that null hypothesis. So, now we have to go back and read. So in 2012, the American Veterinary Medical Association released a report that 36.7% of U.S. households own at least one dog. There's a null hypothesis. But another company, the APPA, believes that more than. That's your null. So if we were going to write this out, our null hypothesis would be, the null is 36.7. I'm not going to write everything out. Our alternative is greater than 36.7%. Well, our p-value is so low, we reject the null and state that there's evidence that the APPA's claim is more plausible. So the data provides significant evidence because we're rejecting that more than 36.7% of households own at least one dog. All right. In 2012, the American Veterinary Medical Association released a report. Okay. Which of the following p-values supports this conclusion? All right. So the conclusion here is the data observed does not provide significant evidence that more than. So if we do not provide significant evidence, that means we failed to reject the null hypothesis, which means that our p-value has to be greater than our significance level. So all the p-values that are greater than would be 0.19, 0.4. This isn't even a real p-value. That's smaller, that's smaller. So, by the way, whenever you do these problems, if you get a p-value that is less than 0, or if you get a negative p-value, or you get a p-value that's greater than 1, you've done something wrong. It has to be between 0 and 1. It can be 0. I mean, sometimes you might get a problem where there's, 30 zeros in front of your after a decimal point, and your Excel can output that as 0. And that's fine. You can get 0. Suppose the following conclusion that the data observed provides significant evidence. So, which of the following p-values supports this conclusion? So significant evidence means we've rejected the null hypothesis. So that means we're less than 5%, or less than 0.05. Well, even though this is significantly close to 0.05, it's still less than. We would still reject. Greater than, less than. Okay. A Gallup poll claims that 48% of Americans support the Affordable Care Act, and college campus survey asks whether or not they support. We have to see, is it categorical or quantitative? Well, if your data is not numerical, like age, height, weight, if you're asking them like a favorite color, we can't find the mean of this, so it's categorical. And we're saying, do you support yes or no? Here, though, we asked, a recent study claims that the average student loan monthly repayment is $351. A phone survey is conducted and asked how much student debt they have. That's quantitative. What's the numerical, value of this? We can find the mean amount of money that borrowers aged 20 to 30 have to pay back. Okay. In a recent Gallup poll, 55% of Americans support the replacement of the Affordable Care Act with a federally funded health care program that provides insurance for all Americans. Congressmen from a certain state believe this poll is not representative of their constituents and that the state percentage is lower than the national percentage, so they conduct a statewide poll. A random sample of 2,000 responses are chosen, showing that 700 of the state citizens support. So for which group are we making a hypothesis? Well, because our sample is only from this particular state, we really can only make a claim about that particular state. So it would be the population of state citizens and not the population of Americans. If we did a random sample of all Americans, then the claims and inferences that we make based on that sample can be extended to U.S. citizens. But because this whole sample is only for state citizens, we can only make claims about that population. What is the proportion for the null hypothesis? Well, your null hypothesis is, if you go back, it's just what the Gallup poll reported, 55%. So 0.55. And what this congressman thinks, it's lower than. So the alternative hypothesis in this case would be that the state proportion is smaller than the national proportion. So in other words, you can represent this symbolically. Our null hypothesis is that P equals 0.55, and the alternative is that P is less than 0.55. There you go. So what does the proportion in the null hypothesis represent? Like, once again, we're not making inferences based on the United States as a whole. We're making inferences based on the number of state citizens. Yeah. Actually, no, it's the proportion, not the number. All right, so what is the test statistic for this scenario? So if you remember, I can write all this out. So our null hypothesis is that P equals 0.55. Our HA is that P is less than 0.55. So when we did confidence intervals and stuff last test, we had to find what's called the standard error of our test statistic. And it's actually the same thing this time. So if you remember, the formula is the square root of P times 1 minus P over N. And one of the things that's important to note with hypothesis testing is that throughout the whole process, you're actually assuming the null hypothesis is true. And we're looking for evidence to the contrary. And so this p-value that we obtain is not the probability that the null hypothesis is true. It's not the probability that the alternative is true. The p-value in these scenarios is assuming the null hypothesis is true. What is the probability that we would obtain a sample statistic that we did, or more extreme? And that p-value allows us to say, oh, if it's really low, well then there's a really low chance we would obtain this test statistic that we did. Therefore, the alternative is more credible, in other words. So we're going to do basically the same thing that we did before with confidence intervals, but now we're going to use the standard error to calculate test statistics. So our standard error is the square root. So we're assuming that the null hypothesis is true. So the square root of p, so 0.55 times 1 minus p, divided by, what is the, can't remember the exercise, 2,000. So divided by 2,000. So once again, we use our null hypothesis value here because while we're doing these significance tests, we assume the null hypothesis is true. So that's our standard error. our z-score is the same as before. It's going to be our sample proportion. So this is really the only time you actually need to use p-hat, is in the test statistics. So our sample proportion is 700 divided by 2,000. So our z is p-hat minus our 0.55 divided by the standard error. And that's a very small z-score. So we want to go back down. What is the test statistic? Rounded to 5 decimal places. So we can use Excel to round, and we output 4. One more. So negative 17.97866. So what conclusions can be drawn from the p-value and or test statistic using a significance level of 0.05? So we can find the p-value here. I'm just going to let you know, don't be surprised when this p-value is very small. So the way that we calculate the p-value is now going to be determined by the direction of our alternative hypothesis. We're looking at a less than probability. We're looking at the probability that z is less than negative 17.97866. And so now we do, because we're assuming normality, we do norm S dist. What's our z-score? Well, here it is. Cumulative is 1. So Excel says that this is, so here's what a lot of students will do at this point. They're going to, if it asks you for the p-value, they type in 1.43. Well, in fact, this is not true because your p-value cannot be bigger than 1. If you look here, it says e to the negative 72. That means we have to move the decimal place over 72 times to the left. So it's 0.71 zeros and then 1. That is probably the smallest p-value that I've ever seen in my life. So this is such a small p-value, we reject the null hypothesis. So the p-value is extremely small. Oh, we can accept the null. We never accept the null. So anything that says we accept the null or accept the alternative, that's automatically wrong. It's all we have evidence to support one claim versus the other, but we never say we accept it. So since the p-value is extremely small, we can reject the null hypothesis. Alright. So in a recent Gallup poll, 44% of Americans support, this is basically the exact same question, so I'm going to skip it. Maybe not. I'll show you how to calculate the p-value because it might be more. Yeah, this is more. It's fine. We can do it. So we're making a, just like before, we're making a hypothesis on a population of state citizens. And now in this case, our alternative hypothesis is 44. But now this congressman is claiming greater than 44%. Which is going to change our test statistic. And it's going to change our standard error because we make our standard error under the assumption that the null hypothesis is true. So we can go back in here and change this 0.55 to 0.44. And then change our sample size to 4,000. Our p-hat is 2560 out of 4,000. And then I'll erase the p-value. So everything else is basically the same. I just changed the numbers I already had in there. So what's the p-naught? That's 44%. The congressman thinks that more than the national proportion. So in other words, we have it typed out right here. Just pay attention to your subscript. So the null hypothesis is that it's equal to 44, and the alternative is that it's greater than 44. And we've already used Excel to calculate the test. I just changed the numbers. I really wanted to show you how to calculate the p-value for greater than. So our test statistic is 11.46706. What's the test statistic for this scenario? Wait, that's why. I didn't change this. I didn't change it to 0.44. Going too fast. So it's our sample proportion, which is 0.64, We got that by just dividing the 2560 divided by 4,000 minus our null hypothesized value over the standard error. So that's 25.48236. There we go. So now in this case then, from our p-value, if we go back to our probability statement written here, our null hypothesis, our alternative hypothesis now says we're greater than. So now we're going to see what's the probability that our test statistic is greater than 25.48236. And remember from our second test maybe, we're going to find the area under the normal distribution to the right of a specified value. So that's going to be 1 minus norm S dis. And then we just click on our Z, comma 1, and it says 0. And that's fine. We can get a value like that. We can probably extend the decimal out a bunch and finally get a different number, but what this means is it's practically 0. Since the p-value is significantly smaller than 0.05, so it is. 0 is essentially smaller than basically everything. We reject the null in favor of the alternative. There's evidence that more than 44%. We can reject the null because more than that. Remember, nothing about accepting or anything like that. Alright, in a recent Gallup poll, 61% of Americans support the replacement of the ACA with a federally funded healthcare program that provides insurance for all Americans. Congressmen from a certain state believe this poll is not representative and the state portion is lower. Which of the following random samples gives the most significant evidence against the null hypothesis? So meaning we want to reject the null hypothesis and claim that it's smaller than 61%. Well, we're just looking to see, we just want to see really here, which of these has the smallest sample size. So all these are 4,000. Well, in this case, it's only 1250. 1250 out of 4,000. That's 31%. That provides significant evidence, more so than the other three, because this has the smallest in favor of replacing the ACA. Alright. A Gallup poll published in 2014 showed that 37% of Americans feel that national defense and military spending is too high. A sampling distribution for the proportion of Americans who this outlook in the range of 100 Americans is shown below. The standard deviation is approximately 0.1. What will the new standard deviation be if the sample size is increased to 1,600? So this all relies on that formula let me erase this. That square root of p times 1 minus p. And it kind of deals with, back on test 3, what happens when you quadruple the standard deviation and things like that. So basically, to go from 100, our sample size is initially 100, and we've increased it by 16. That means we've increased our standard deviation by a factor of 16. You can just divide the two. So if you think about your formula, we'd be increasing our sample by a factor of 16. That n value is in the denominator. So we can take the square root of 16. You get 4, you know why I just typed in there. Well, that means that our standard deviation is going to be reduced by 1/4. So we can take 0.10 and divide it by 4. And we get our new standard error deviation of 0.025. And so the way that we think about this one again is we've increased our sample size by a factor of 16, which means we reduced our standard deviation by a factor of 4. And so we just take our old standard deviation, divide it by that factor, and we're done. And it should make sense. Increasing the sample size is good. We want a more representative sample of our population. So increasing the sample size will reduce the variability that we observe. Alright, a Gallup poll published 37%, the standard deviation is approximately 0.1. Suppose a sample proportion of 0.43 is observed. How will the test statistic be affected if the sample size is decreased? So same idea, we can think of that formula. So our test statistic has our null hypothesis, so it's basically p hat minus p over the standard error. So the standard error is the square root of p times 1 minus p over n. So let's just think of that just by itself. The square root of p times 1 minus p divided by n. So if we reduce the sample size, that means the number in the denominator of our standard error is getting smaller. Well, if this number is getting smaller, when the denominator gets smaller, the overall value of the fraction increases. So if reducing the sample size is going to increase our standard deviation. And that should make sense because if we increase the sample size, the variability decreases. So decreasing the sample size will increase the variability. But with our test statistic, it's p hat minus p over the standard error. So if our denominator is getting larger because of the reduction in sample size, that means the test statistic is getting smaller. A lot to think about. Alright, a Gallup poll published in 2014 shows that 37% of Americans, standard deviation 0.1. Suppose a researcher believes this proportion is larger. What proportion would provide the most convincing evidence against the null? So our researcher believes that it's larger than 0.37. So we're just looking to see which of these is the highest. Which of these is farthest away from 0.37 in the right direction. So 0.438 is pretty high. That is the highest. So that would provide us the most evidence. Okay. A Gallup poll published in 2014 showed that 28% of Americans feel that national defense and military spending is too low. Which of the following samples meets the minimum sample size criteria for z-test against the null hypothesis 0.28? So one of the things I said earlier when we were calculating the p-values and the test statistics for that American Affordable Care Act problem is that the sampling distribution is approximately normal. Now, we can't always, it's not always approximately normal, and there are some things that have to be, some conditions and assumptions that have to be met. And the biggest one in terms of the shape of the sample distribution being normal is that n times p has to be greater than 10, and n times 1 minus p has to be greater than 10. We have to check both. So we want to see our sample size. So we basically can rewrite this equation and solve for n. So to get that, in this case, we would divide 10 by our p-value. So 10 divided by 0.28. This first condition tells us that our sample size has to be bigger than 35.7, or 36. Let me see, where were we? And then now, we basically do the same thing. Now we're going to do 10 divided by 1 minus 0.28. So one of these says that our sample size has to be bigger than 14. The other one says our sample size has to be bigger than 36. Well, take the higher of the two. Because if it's higher than 36, it's automatically higher than 14. So every sample larger than 36 we can do. So that's good. That's good. That's good. And that's good. Right. Is this the same question I did before? Alright. Well, let's just do this first part. I can do it. It's no big deal. The more questions I do, the better you guys will feel. So in a recent poll, 63% of Americans support the replacement of the Affordable Care Act with a federally sustained idea. Okay. So our null hypothesis in this case is that P equals 0.63. Okay. 0.63. And the alternative is that P is, Congressman, lower, so 0.63. And then he takes a sample, P hat is 1,475 out of 2,500 support replacement. There's our P hat. So now we want to see, can a test statistic be used to find evidence against? Well, what they mean by that is, are those two conditions that we looked at last example, are they met? So we need to see, T out P. We need to check what is n times P and what is n times 1 minus P. So n times P bigger than 10. Yes, it is. N times 1 minus P bigger than 10. So because these are both greater than 10, yes, we can do this. We can basically say that the sampling distribution of P hat is approximately normal. So calculate the test statistic. So our test statistic, we first have to find the standard error. That's equal to the square root of P times 1 minus P over n. Now remember, we're not using P hat yet. It's all assuming the null hypothesis value is true. So 0.63 times 1 minus 0.63 divided by n. Standard error, now you find z, now we use P hat. So P hat minus T divided by n. And then we want just 6 decimal places. That's 1, 2, 3, 4, 5, 6. And yes, test statistics can be negative, p-values cannot. What before? Oh, what was I doing? I didn't have the right thing. 9. Negative 4.16 decimal places. I'm going to do some weird. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay. So negative 4.142. 465. There we go. And then p-value. So the p-value calculation is determined by the alternative hypothesis for testing less than. So we just use regular norm dis from sdis, and then type our z-value, comma 1. And we want scientific notation, which, here we go. So now the 2 decimal places after the decimal point, so we have 1.72 times 10 to the negative 5. That's what this means here. And that just means move the decimal to the left 5 times. But what conclusions can we make here? Well, the p-value is still very low, so we reject the null hypothesis. Since the p-value is less than 0.01, we can reject the null hypothesis to conclude that less than 63%. Remember, any of these statements that involve accepting the null hypothesis, ignore those. What hypotheses and test statistic best fit the curve below? Well, we've shaded, so basically, this p-value we find is the area under the normal distribution. So in this case, we're greater than 1, so that tells us our alternative hypothesis is greater than something. And actually, it's greater than 1, so that means our z is 1, and we're greater than some value, so it has to be this one. And I got 1 by this one right here. So in this one, if you look, we shaded to the left of negative 1, so that tells us our z is negative 1, and our alternative is less than because we shaded to the left. And the next one should be 2 tails. There it is. So sometimes, we haven't seen this yet on these problems, but throughout your homework, I'm sure you guys have seen it. We often don't have to specify the alternative hypothesis as strictly less than or greater than. Sometimes you're just interested in, is it not the value that we know hypothesis claims? So when that's the case, we actually take the absolute value of the z-score and consider both extremes, less than and greater than. So in this case, we're looking for z is less than negative 1 and z is greater than 1. So that looks to be this one. Let's double check. No. Oh wait, no, it can't be that one. It's going to be that one. So if we shaded both ends, we should have our alternative hypothesis not equal to. Yeah, see, don't fall prey to this. Because we're shading both tails, that tells us our alternative is not equal to. Okay, well, that might be it for proportions for a little bit. Now we're moving on to means. Delete all this. So I'm just trying to keep it organized for you guys so you can follow pretty easily. So, the bar graph below illustrates consumer price index differences between the second quarter of 2015 and the second quarter of 2016. Consider the CPI decrease in beef and veal at 6.4. So that's going to be our null hypothesis, is that, now we're dealing with means now, so we use mu, I'll just use u, but it stands for mu, the population mean. So equals 0.0064. The alternative is that mu is, certain State Department believes that the CPI decrease of beef is less than 0.0064. They obtain, so I'm going to write everything up. They obtain a sample of a random sample prices from these two periods at times 140. And find that their X bar, their mean decrease was 0.0061. Assuming the population standard deviation is known, what conditions are true of whether or not a z-test can be used in this scenario? Well, the whole point of, so if you remember from last test, maybe that was last test, I can't remember. So there are two types of tests with means, either a z-test or a t-test. And the main distinction between the two is whether or not your population standard deviation is known or unknown. So if your population standard deviation is known, you can use a z-test. If the sample standard deviation is used, you use a t-test. Now, we also have to make sure that our sample size is large enough. And the cutoff is 30. So if our sample size is also bigger than 30, we can do a t-test, or a test. And that's known as the central limit theorem. You might see that abbreviated as CLT. And that just means once our sample size is roughly 30, for means, we can claim that our sampling distribution for the mean is approximately normal. So in this case, the sample size is large enough to conduct a z-test because n is greater than 30. Sample size is too small, that's not true. It is known that the variable varies normally in the population, so a z-test. And then the sample size is large. Well, we can do this. And it's a z-test though because we know the population standard deviation. If we were given the sample standard deviation, we would actually have to use a t-test. So, that's all we need to do. Okay. So in this case, what do I have to do with this one? That's it? Okay. Just a hypothesis. Alright. So, they believe the null hypothesis here is consider the CPI decrease in beef at 5.6%. So, that would have been 0.064, not 0.064. So now, our null hypothesis is that we're equal to 0.056, and that's that mu symbol. And then our alternative would be less than. Is less than 0.056. And so hopefully you're getting used to the pattern now to see that the null hypothesis is always our equality, and that we're using less than, greater than, or not equal to in the alternative. What do I do with this one? It's basically the same thing, but so consider the CPI decrease in beef is 6.5%, so that's our null hypothesis is that mu is equal to 0.065, and a researcher believes that which is not 6.5%. It doesn't matter the direction. We just think that it's not that value. So that means our null is 0.065, and our alternative is not equal to 0.065. Alright. So this is where we do everything. Okay. So we're going to find the test statistic here. So our null hypothesis value is that mu, in this case, equals 0.059. The alternative is that mu is less than 0.059. Our n is 100, and then our x bar is 0.056. So that's what we're given here. We're also given that sigma, the population standard deviation, is 0.004. And this is really the big thing here. We're using a z-test because of the population standard deviation being given to us. And that's really important because later on when we get to not having the population standard deviation, if you use a z-test, your whole answer is going to be wrong. So the first thing we want to do is calculate our standard error, just like with proportions. And we're going to do, the formula is a little different. The formula is the standard deviation divided by the square root of the sample size, sigma over root n. So that's our standard error. And then our z-score is just a proportion, but this time it's going to be x bar minus mu. Now the mu is the value specified in the null hypothesis. So that's what we assume to be true, divided by the standard error. Is that even? Alright. Negative 7.5224. Alright, next example. A bar graph below displays illustrates the percent change in major consumer price index categories from 2011 to 2015. The graph shows an 8.1 increase in the food category and one state department. True. They conduct a random sample of prices from 6 restaurants and 6 grocery stores. Are the conditions met? Well, we have to think. What's our sample size? Our sample size is 12. No. So our sample size is too small. Whoa. Yeah, it's the same question over and over again. Alright. So, in this case, same question, but now we're considering the CPI increase is 3.1%, so 0.031. The HA then is less than 0.031. Our N is 450. Our X bar is 0.029. And sigma is 0.03. So our standard error actually doesn't change. Well, it changed for us, but we have to be careful now and say with our z-score, it's going to be our X bar minus our null hypothesis value, which is 0.031. So there's no z-score, but it actually doesn't want that. It wants the p-value. So the p-value, we look at the alternative hypothesis, less than, so the north S diff, that calculates arrow to the left, calculate the z-score, done, to 4 decimal places. There we go. Alright. So this one, everything's going to be given to us. So the graph shows an 8.5 increase in the food category for the nation, and one State Department of Agriculture believes the increase is less than 8.5%. So really the same, almost same exact question. So 0.085 is our null hypothesis. The alternative is less than 0.085. We've sampled 150, so we did 75 restaurants and 75 grocery stores, and find that our X bar is 0.081, and the population deviation is 0.03 again. So our standard error is good. Here it just changes to 0.085. And then, what is the p-value? Well, because everything was already typed in, and I showed you how to type it in the last question. I'm not going to really go over it, but that automatically gives us a p-value around the 4 decimals of 0.0512. There we go. Alright, same question, just now we're looking at, the graph shows an 8.8% increase, so 8.8 is 0.088 as our null and as our alternative. They conduct a sample of 480. What's our sample? X bar is 0.091, and actually our alternative is more than as well. They believe it's greater than 8.8%. Sigma is 0.04. And so everything is good except our z-score needs to be 0.088. Be careful here. I mean, pay attention to the fact that our p-value is created based on a less than alternative on the last example, so we're now testing more than, so we want to do 1 minus. 0.088 0.0502. Now, even though this p-value is seriously close to 0.05, it's very small. It's slightly above it. We would still fail to reject the null hypothesis in this case. 0.05 is our cutoff. 0.0502 is just slightly bigger. It doesn't matter how close it is. As long as it's bigger, it is fail to reject. All right. I'll do this one because the hypothesis is different. So the CPI decrease in beef is at 5.8%, so 0.058. We're looking at a not equal to. Not equal to. That makes no sense, but that means not equal to. So our sample size here is 300. X bar is 6.1. Sigma is, I guess I'll give it to us later. Actually, okay, so as we go through the question, that's hard to do, never mind. So the null hypothesis is that we're equal to 0.058. The alternative, if you look, is not equal to 0.058. Okay. Luckily, they give us everything here, because these questions get kind of repetitive. With a p-value of 0.041, what conclusions can be made? Well, 0.041 means we reject the null hypothesis. So what is the null hypothesis? Well, it says consider the graph shows an 8.1 increase in the food category. So that means our null hypothesis is that the increase is 8.1. And then our alternative is they believe an increase. So they believe it's greater than 0.081. So we fail to reject because our p-value is given to us as 0.041. So we reject the null hypothesis in favor of the alternative. Then it is surprising to observe data like these, well, assuming the null hypothesis is true. Therefore, the results are significant. We have enough evidence to accept, nope. Accept the null, automatically no. To reject the null. So the p-value is less than 0.05. So that value means, assuming the null hypothesis is true, there is a 4% chance that we would obtain a test statistic as we did our work stream. That's unlikely. It's unlikely to happen by chance, and that's what this little first sentence means. It's surprising to observe data like these. Checking for a while. Wow. Alright, well, we'll let that one kind of do its thing. We'll come back to it. Okay. Yeah. Alright, I think there's a problem with that question. Let me exit and go back in. What question number is this? 31. Alright, so test for non-credit. Let me just go back in and make sure. Alright, 31. And we were right here. Oh, there's that question again. So I should check answer. And it was right. Sometimes emails have issues. Alright. So the APPA has been gathering statistics on pet ownership in the U.S. since 1988. They published the results of their national survey on a biennial basis. Their report stated that dog owners spend an average of $1,436 per dog. The American Veterinary Medical Association, established in 1863, believes the amount is less than. They publish the results of their U.S. pet ownership and demographics, first like every 5 years. Their 2012 report said that dog owners spend an average of $227. Wow, big difference. If the APPA survey represents the population and the AVMA source code represents a sample, what are the null and alternative hypotheses? Well, we want to look at the null is that mu is equal to 1436, and the alternative is going to be less than 1436. They believe it's less than. That's based on the population. So, the AVMA, let me just write these in, just so we can kind of see this. Let me just scroll. So, we believe our null is that mu is equal to 1436. The ha is that we are less than 1436. And, so their X bar is 227. Alright, that's all I know so far. So the AVMA data collected from 88,000 veterinarians. So that's N, 88,000. And then the supposed sigma is 427. What's the test statistic? So our standard error, we still do the sigma divided by the square root of N. 88,000. Our z-score, we still do x bar minus the value in the null hypothesis, 1,436, divided by the standard error. And our p-value is going to be not 1 minus. I'll just go to that in a second. So our test statistic, is it really that? That makes sense. 839.92356. Woo! Man. The variance between the population mean and sample mean is quite unusual. And both the APPA and AVMA and the APPA include surgical procedures in their calculations, while the AVMA only includes routine vet visits. Without surgical procedures, our null hypothesis is now transformed, is reduced to 27.5. And that means we're now mu is greater than 227.5. And then sigma is now 100. And now our test statistic is x bar minus 227.5 over the standard error. And that's our new test statistic, which is better. So it's negative 1.48324. There you go. All right. So, the brake pad manufacturer of 12 millimeter brake pads uses equipment that goes through routine maintenance. The width of the brake pads vary normally with a standard deviation of 0.01. Prior to the next scheduled maintenance, a shipment of 1250 brake pads is found to have an average width of 12.02. Can we conclude the equipment needs maintenance sooner than expected using a 95% confidence interval? So, alright. So, confidence interval. So the first thing we need is a point estimate, an X bar, which they give us. A shipment of 1250 brake pads found an average width of 12.02. So 12.02 is our X bar. It's our sample mean. And we know that our population standard deviation is our sigma, if you want me to call that. Either one is 0.01. And our N is 1250. That's actually almost all we need for this problem. We also are going to need a z-score. And that z-score is used in the margin of error. So if you don't remember how to find your z-score, you can use inverse norm or norm inverse, norm S inverse, and the probability. Well, if you remember, so confidence intervals, we want the middle 95%. So what we're going to do is we want 95% to be in the middle of our interval, which means we have 5% in the tails. So we're going to do 1 minus, now it's 2 tails, we're going to do 0.05 divided by 2. And that 5% comes from 1 minus 0.05. And if you note, if you recognize that as 1.96, which is the z-score for 95% confidence. There are three values you can really know for z-scores. So z90, z95, and then z99. So for 90% confidence, you can just automatically use as the z-score is 1.645. 95% is 1.96, and the z-star or z99 is 2.5758. And I just memorize them. You don't have to, but it's just easier. It just saves you a step. So with confidence intervals, we first need our standard error. And the standard error is calculated exactly like it was with those hypothesis tests that we just did. It's going to be sigma divided by the square root of n. So standard error, now we need the margin of error. And the margin of error is found by taking that z-score and multiplying it by the standard error. And then, lastly, to get our lower estimate and our upper estimate, we take our x bar, our point estimate, we subtract the margin of error, and then we take our point estimate and we add the margin of error. And what this tells us is we are 95% confident that the true width or the true size of a brake pad is between 12.01 and 12.02. Well, what's our hypothesized value? What are we looking at? Well, we're looking at the brake pad should be 12% or 12 millimeters. This tells us that they're actually probably bigger. There's more evidence here that it's probably bigger. So, does the equipment need maintenance? Yes. Because 12 does not lie inside that interval. If 12 lied in it, then yes, we're good. But because this is completely above 12, we have to say that there's probably evidence that it needs maintenance. All right. Clean it up. In 2010, Taco Bell, let me copy and paste this. Suppose the equipment, okay. In 2010, is this all enough to do with it? Oh no, it's all of it. Alright. So in 2010, Taco Bell has 5,600 locations across the U.S. with an average annual sales of, what is that, 1,284,000 per store. Assume the sales of a store vary normally. With various locations opening and closing since 2010, remodeling and menu optimization, QSR Magazine believes the average sales have increased. So we're going to take a random sample of the average annual sales over the last few years. All right, and here we go. Now, note that we see this letter T here. Don't let that fool you. Our null and alternative hypotheses are always in terms of mu, or P, depending upon the problem. So, we say that the average sales mu is equal to 1284, and then we're looking to see, we believe the sales have increased. Aha. We can go ahead and write this in if you want to. So that's equal to 1284. The alternative is that mu is greater than 1284. Note that it didn't give us anything else in the problem, whereas the other examples gave us a population standard deviation. This, in fact, did not. We're going to make claims entirely based on the sample that we're working with. So, what form of hypothesis testing would fit this scenario? Well, a t-test, not here it's giving you the option of 0 t, and you have to figure out which one is it. Well, the population standard deviation is not known. That is why we need to use a t-test. And also note that it did say that the population was normal. That is why it's a t-test. So the population is normal, but because the population standard deviation is not known, we have to use a t-test. Alright, so calculate the test statistic for the hypothesis test. Well, since we're working with our data, we need to find two things, the mean and the standard deviation. And so because we're going to use a sample standard deviation, that's why we're using t. So the mean, we do it as average of these four for these 5 things. And then we do our standard deviation, stdev.f, highlight our data. So we have our sample mean and our sample standard deviation. And then n is, where is that? N is just the sum of all that. Or we can do, oh, that's fine. N equals the sum, if sum, actually no, it tells us how many these samples. 5,675 locations. Big sample, average, alright. We need to do the n. Well, I guess n is just 1, 2, 3, 4, 5. 5 locations. 5 regions. So, calculate the test physics for this scenario. So, we need to first find the standard error. Standard deviation is the standard deviation divided by the square root of n. 55.207. And then our z-score is, just like before, it's going to be our mean, our x bar, minus the value in the null hypothesis, so 1284, divided by our standard error. So test statistics are into 5 decimal places, so we can use it spelled around if we're not good at it. 1, 2, 3, 4, 5. 0.63760. And then what's the p-value? So p-value, remember, is determined by the direction of the alternative hypothesis, so we're going to be greater than, so it's 1 minus norm S diff z-score, 1. Woo! 4 decimal places. 0.2619. Those are 4 decimal places. The z-score was right, correct. And this guy believes the averaging of sales has increased. Oh, duh, that's why. So I did something that everybody always does. And let's just say that I did it on purpose. So note that was wrong. What did I do here? So we were using a t-score, and a t-distribution is not a normal distribution. It's very similar, they're both symmetric, but the t-distribution actually has thicker tails. And so the way that we calculate the p-value for this test using the t-distribution is we just use, instead of norm dist, we use t-dist. What I love about the t-distribution stuff is it actually automatically will calculate direction for you. You know, with normal distribution, you had to worry about, was it a one-sided test or a two-sided test, and if it was right-tailed, you had to do 1 minus. Well, t-dist has 3 options. t-dist, t-dist.2t, t-dist.rt. And because we're looking at a right-tailed test, that's what RT means. And it tells you what's X. Well, X is our t-score. Now, degrees of freedom is a new thing. Just for simplicity, the degrees of freedom is just, it really dictates and determines the shape of the t-distribution. And in this case, the degrees of freedom is always your sample size minus 1. So 5 minus 1. Enter. And that's our p-value. No, it's kind of close to the one we had before. I think it was about 2619. But because it's actually a different test statistic with a different distribution, we actually have to account for the fact that the t-distribution is necessary. So, but the conclusions out of this one are the exact same. Because our p-value is greater than 0.5, we fail to recheck the null and say that the average annual sales is still about 1,000 or 1,200,000 per thousand. So p-value is greater than 0.05. Our results are not statistically significant, and we cannot reject the null hypothesis, and we cannot conclude that the average sales is greater than. There we go. Worry. Alright. I'll get a new sheet. Next problem. Why did that happen? Another type this in. try it one more time. Yep. So we'll do M5, 1, 2, and so drag it. Alright, one more. So our table has gender and age, 65.2, 78.7, 91.2, 34.8, 62.2, 83.9, 61.5, 77.6, 89.7, and 84.6. Alright. So the life expectancy of an American in 2013 was approximately 61.1. The life expectancy variable varies normally, but the population standard deviation is unknown. So because the population standard deviation is not known, we can't use a z-score or a z-test. So a researcher wants to know whether life expectancy has changed from 2013 to the present year. She selects a sample of 5 men and 5 women who have passed. For a man who was 34.8. So we want to know our mu, or our null hypothesis that mu is 61.1. But we're looking to see, has it changed? Now, it doesn't really specify did it decrease or increase, so we're just looking to see, well, is it just not 61.1 anymore? Oh, I did the wrong thing. Oh my gosh, not paying attention. Mu is 61.1. The alternative is that mu is not anything about t. Not equal to, equal to. Pay attention to your subscript. Alright, so what kind of hypothesis testing would best fit this scenario? Well, it's a t-test because the variable varies normally and the population standard deviation is unknown. So we'll do this one. Good. So in this case, our n is 10, 5 men and 5 females. We need to find our x-bar and we need to find our standard deviation. So our x-bar is the average of our sample. Our standard deviation is stdev.s of our sample. Remember, it's stdev.s, not .t. And then we need to find our standard error and then our t-score. Not z. So standard deviation is the standard error standard deviation divided by the square root of the sample size. And then our t-score is x-bar minus the value in the null hypothesis, which is 61.1, divided by the standard error. So it is how many decimals? 5. So we do 2.16727. There we go. Now for the p-value, remember we're using the t-distribution now because of sample standard deviation, so it's t-dis. But if you remember, our alternative hypothesis is not equal to, so it's a two-tailed test. And then we type in our t. Our degrees of freedom is 10 minus 1. And there's a p-value, 0.05 decimals, 84. And you can use Excel around if you want to. Remember, that is up here with these two. So, what conclusions can be drawn? Well, our p-value is actually larger than 0.05, even though it says 0.05 here, but pay attention to these decimals. So, because our p-value is greater than, we fail to reject the null hypothesis. I'm not thinking enough, we cannot reject the null and cannot conclude that it's not 161. There we go. And so that's what's interesting about statistics, because our sample, we only sampled 10 people, and we got the average life expectancy is 72.94, which is, a lot bigger than 61.1. But accounting for, variability and things like that, we actually can't say that it's actually larger than 61.1. Alright. Let's talk about over here. Nice. I'm going to go back to that sheet and just do it this way. So this one is 1304, 1295, 1492, 1344, 1159. So in this one, our null hypothesis is that these stores make 1,188,000, and we think now that maybe, a certain couple number of years later, it's less than that value. So that's our null and our alternative hypothesis, that mu is equal to 1488, and our high is that mu is less than 1488. There you go. What form of hypothesis testing would best fit this? Well, that would be a t-test, because the average fails very normally and the population standardization is unknown. And really, everything is now calculated for us. I did the mean, it's already done. Our n is once again 5. Our standard error is this thing, but I have to change this now to 1488. So the test statistic is negative 3.17066. And remember, p-value, though, we have 3 functions for t. And this is a left-tailed test, so we just do basic t-diff. That's automatically left. So negative, that degrees of freedom is 4, and then cumulative is 1. And then 0.0169. 4 decimal places. So now, because 0.0169 is less than 0.05, we reject the null hypothesis. Our results are statistically significant. Since the p-value is greater, since the p-value is greater, since the p-value is less than 0.05, we can reject it all and conclude that the average is less. Good deal. Alright. Well, this is nice. This one basically gives everything to us. So we have our mu0 is 138.5. Our x bar is 143.1. Our s is 25.1. N is 150. So we want to calculate a p-value and a test statistic. So test statistic, we do standard error first, and then we find t. So it's s divided by the square root of n, and then t is x bar minus mu sub 0, mu naught, divided by the standard error. And how many decimal places? 4. So 2.2446. So in the p-value, pay attention to the alternative hypothesis. It says it's not equal to. So we're going to do t-dis dot 2t. T, our degrees of freedom is 149. 1 less than 150. So 4 decimal places, 0.0263. Let's see, do we need to do this one? It's basically the same thing. They give you, I'm not going to do it, so they give you everything you need to know. Just calculate the way that we've been doing it. Alright, this is actually what I wanted to get to. 2 sample proportion problems. Alright, so a pharmaceutical company tests its new product to reduce joint pain on 1,000 people. So some of you are given the drug, some of you are given the placebo. So, this one's pretty good. So we have, now we're moving on to 2 proportions here, and kind of making inferences about the difference of proportions. So, really we have 2 groups here. We have people getting a drug and people getting a placebo. So our p-hat1 is the people who are given the drug, and 571 of them do not feel joint pain. Of the placebo group, which was 300, 144 out of the 300 did not feel any pain. And so what we're looking for is the formulas reported as effective, control group, be the placebo, find the difference. Alright, so to find the difference, it's just subtract the 2. Do 1 minus the other. 4 decimal places, so 0.3357. And then we're done. assume the treatment effect is a 40% increase in joint pain relief with a standard error of 7%. What analysis and conclusions can be drawn? Select all that apply. 3 standard errors of the mean. Alright, so here's our value. I'm going to move this over. And that's our P, I'm going to call it P sub D, P for difference, or D for difference. So, assume the treatment effect is a 40% increase in joint pain relief with a standard error of 7%. So, the sample produced that's not it. So the sample produced a 33.57 increase in joint pain relief. The difference in sample proportion is within 1 standard error of the mean, so the result is not surprising if the treatment effect is really is 40%. So what this means is that, so they're saying assume that taking the drug actually does help with joint pain. So what we can do is we can do 0.40 minus the standard error of 0.07. I gotta do an equal sign. If you think about your normal distribution, think of your empirical rule. 95% of your data is contained within 1 standard error. 68% is contained within 1 standard error. 95 is 2, and then 99.7 is 3. So if we have our population increase in joint pain relief is 40%, with a standard error of 7%. So going 1/3 error to the left means 33%. And our value is right in there. We're close to the mean, which means getting a sample of 0.33% or 33.57% is actually, we shouldn't be surprised by that. We would expect that by chance alone. What is the actual standard error of the differences in sample proportions? So the way that we can do this is, let me just write 2 more things. N1 and N2. N1 was 700, N2 was 300. So what we want to do is, we want to find our standard error. Well, the standard error is the square root of P1 minus P over N. But now we're dealing with 2 proportions. So it's going to be P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 over N2. So we're saying we're adding basically 2 of them together. And that's our standard error. 6 decimal places, so 0.1, 2, 3, 4, 5, 6. There we go. And then how does the actual standard error affect your conclusions from the previous part, if at all? So the increase in joint pain relief falls very closely to the 5% significance level, therefore we can make the decision to reject. The increase in joint pain relief still falls within 2 standard deviations of the mean, therefore no change to the conclusion. Let's just see. They're saying, let's just do 0.40, and let's look at, so our hypothesized value is 0.4. So let's just see. Let's go 0.4 minus 1 standard error. Let's do 0.4 minus 2 standard errors. And then let's do 0.4 minus 3. So, okay, I'll write that down. So 0.3357 was our difference. I erased that, sorry. So if you look here, our value is basically now contained within 2 standard errors of the mean, 0.3357, 0.3352. So because we're 2 standard deviations, it's still not that atypical. We wouldn't be that surprised. So we went from being within one standard error of the mean to 2. And that's still, if you think about the empirical rule, or the 68, 99, 95, 99.7 rule, is still, plausible. Alright. Where's all this? Okay. Suppose an experiment is conducted. What is the increase in the population of affected subjects from P1 to P2? Well, they give us everything. P1 is 0.88, P2 is 0.45. So P1 minus P2 is what we're looking for. So increase of 0.43. What question number are we at? 41. Suppose an experiment is conducted repeatedly with treatment groups and control groups. Let P1 be the mean of the sample proportions of the treatment groups that were affected, and P2, what is the standard error of the mean of the differences? Okay, so standard error is just that formula that we've always been working with. P1, let's do N1, P2, N2. We need these three things, or four things. So P1 is 0.67, N1 is 900, P2 is 0.49, and N2 is 600. So the standard error is the square root. Now with one sample stuff, it was, just to reiterate, it was P times 1 minus P over N. I don't know what. But in this case, we have two proportions, so it's going to be P1, 1 minus P1 over N1, plus P2 times 1 minus P2 over N2. So P1 times 1 minus P1 divided by N1, plus P2 times 1 minus P2 over N2. Done. 6 decimal places. 1, 2, 3, 4, 5, 6. We are good to go. And now what's nice though is because you're clicking on this, so when you take your test, click it like this once, or like, input it, because if there's a question that's basically similar, just type your numbers in. So in this case, it just says, basically read the whole question, 0.87, 900, 0.49, 500. Well, there's your new standard error, 0.025009. Alright. Which formula is actually the standard error of the differences in two population proportions? When these sample proportions are given, well, it's just what we wrote down before. It's going to be not this, not this, not this. That's what we did here. It's P hat, or P hat 1 times 1 minus P hat 1 over N1 plus P hat 2, 1 minus P hat 2 over N2. And I know that I'm writing P1 and P2 here. I'm writing that just for simplicity, just to kind of save me the 3 seconds it would take to type the word hat. But just know that I do refer to these sample proportions themselves and not, population parameter values. A researcher is trying to determine a 95% confidence interval to estimate a treatment effect using the data below. So, here's what we need. So, to find a confidence interval, we have to do everything we've done before. Basically, finding the standard error first. So, in this case, our P1 is 0.64, N1 is 1,000, P2 is 0.472, and N2 is 750. So the first thing I want to talk about is, what's our point estimate? Well, our point estimate is just the difference of the two values. That's our point estimate, whereas P1 and P2 were separately point estimates. Now we're looking at the difference. So our point estimate for the difference in proportions is 0.64 minus 0.472. Then we need to find our standard error, which is that long formula, square root of P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. And then now we need to do a confidence interval, and it says to use Z as 1.96, which if you remember from a couple problems ago, a 95% confidence interval with Z, we use Z as 1.96. So our margin of error is Z times the standard error. And then we can get a lower bound and an upper bound by taking our point estimate, subtracting. Oh, I don't even want all this stuff. I'm just going all out. So actually, stop there. Our margin of error is 5 decimals, 0.04649. Yes. Okay. Now this next one, we're going to do the same thing. Now, I've already typed everything separately, and just to show you what the answer is, just so you can kind of see, 0.0642, N1 is 200, P2 is 0.652, and I've got to change that to 0.6, and then 200. So our estimated difference is negative 0.01. Standard error, Z is now 2.576. So our standard error, our margin of error is 0.12310. Alright. Suppose a researcher conducts an experiment with varying sizes of treatment and control groups. A 95% confidence interval is used to estimate the treatment effect. Which confidence interval suggests that there was a treatment effect? So what that means is that was the treatment effective in reducing, whatever disease? Did survival time increase? Did it reduce headaches longer? I don't know. Now, with these problems, though, when we find the difference, if the treatments are the same statistically, that means their difference would be approximately 0. So what we're looking for is if there is an effect, we would expect that the interval would be entirely negative or entirely positive, meaning 0 is not in the interval at all. So this one's entirely positive. This one's entirely negative. This one's entirely positive. That is both, and that's entirely positive. So a treatment effect just means that 0 is not inside the interval. Okay. So a researcher conducts an experiment with a treatment and control group, each of which consists of 20 random people from all 50 states in the U.S. 46% of the treatment group obtained the desired effect. Okay, so P1 is going to be 0.46. P2 is going to be 0.38. Now, be careful with N1 and N2. It's 20 random people from all 50 states, so it's going to be 20 times 50, so 1,000. So our difference here is just P1 minus P2, 0.46 minus 0.38, and the standard error is the same as before. Square root of P hat 1 times 1 minus P hat 1 over N1 plus P hat 2, 1 minus P hat 2 over N2, which we get to be, just for the sake of time, 0.02200. Now, the condition that has to be met in order for the normal model to be a good fit is the same one as before, but now we have to check it twice for both. All NP1s have to, n times p has to be greater than 10, and all n times 1 minus p has to be greater than 10 for both. So, we'll do that. N1 P1, N1 1 minus P1, N2 times P2, N2 1 minus P2. So, P1 times, so P1 times N1, 460, N1 times 1 minus P1, so 540, N2 times P2, and then N2 times 1 minus P2. And all those are greater than 10, so very good. So 460, 540, 380, 620. Okay. So estimate the treatment effect with a 95% confidence interval. So we've actually found basically everything we need. We found P1 minus P2. We already have it in there. We've checked our condition. Standard error we found before. So Z is 1.96. So now we can find our margin of error, which is Z times standard error. And we can find the lower and the upper bound. Always do lower first. So it's the point estimate minus the margin of error. And then it's the point estimate plus the margin of error. And we want 5 decimal places, so we're good. 0.03688, 0.12312. Now, does the interval suggest that treatment effect is effective? Yes. Why? Because 0 does not lie in the interval. $48, $49, $50. Alright, let's do this. Almost there. So, suppose a new virus emerges that affects the U.S. population. A study of 5,000 random males and 5,000 random females. Alright, so N1 and N2 are 5,000 each. So, males, 4.03, so 0.00403, converting that to a decimal, of the males contracted the virus, and 0.00309 of the females contracted the virus. Now look, our conditions are still met. Now, unless the problem specifically says check the conditions, you don't have to check this. But we really need this to be met in all the problems we do in order to assume normality. So we're going to do the difference is this. Actually, I don't know why I keep saying double zero. There we go. So then now our difference is 0.0094. So if you look, that should be P1 minus P2. Standard error is still the same. Calculations, P at 1, 1 minus P at 1 over N1, blah, blah, blah. Z in this case is now, because we're doing a 90% confidence interval, is 1.645. And it counts as a margin of error for us, and it counts our lower and upper. So 0.00345 decimals, 0.01549. And there we go. So, what does this confidence interval mean? Well, if you remember from the last test review, I kind of did a little applet to show what a confidence interval means. It means in the confidence level for a 90% interval in this case means in the long run, if we calculate many intervals in the same way, 90% of the intervals will contain the true population difference in proportions. Now, interpreting the interval itself means we are 90% confident that the actual, we are 90% confident that the actual female infection rate is 0.3 higher than the actual male infection rate. So let's say we did, males minus females. So the male infection rate is approximately 0.3% to 1.5% higher than the female infection rate. There you go. And then we can just convert these two percentages. Alright. Let's just do this. Everything's checked in. And just to save ourselves some time, we're going to just utilize the fact that we've already had this, I've been clicking around. So we have two populations where CDC uses several surveys to measure the vaccination rates for vaccines recommended for different groups. Child VaxView provides data for vaccinations for ages 19 through 35 months. A researcher wants to investigate the difference in vaccination rates between poverty levels. So she uses a random sample of 1,050 families above the designated poverty, so 1050, and 1,050 below. And the people above poverty, their proportion was 0.7874. And below, it was 0.3482. Wow. Note that, I don't know why this is giving me a warning, B4 times B3. I don't care. I'll just leave it, it's right. So, all of these are bigger than 10, and it says a null model is a good fit for the study because all these are greater than 10. And then we're looking for a 95% confidence interval, so that means that Z is 1.96. And everything else should be the same. Here's our point estimate for the difference. So that tells you that that 44% more of in the stable, 44% more of the above poverty families vaccinated. It calculates standard error, square root of p hat 1 minus p hat 1 over n1. Z, margin of error, lower upper. But what that means is 40122 and 0.47719. That is the 95% confidence interval for the difference. So there is strong evidence that the above poverty households have a different rate, 0 to 9. Last question. I think yes. So, a researcher was interested in the effect that professional resume writing services had on applicants being hired. The researcher surveyed 500 total applicants across 20 random companies from the U.S. 28 of the 134 said that they used professional resume writing services were hired, and 35 of the 366. So, P hat 1 is, actually N1 is going to be 134. P2 is going to be 366. And our P hat now is going to be 28 out of 134. And then P hat 2 is 35 out of 366. And note, all of these are still greater than 10. So we're still good. And then now our Z is 1.645. So, for the difference in proportion of applicants who were hired. So our lower estimate is 0.05026. Let me decrease this by 1. 0.17639. There we go. So interpret the interval. So there's a 90% chance. Nope. If you ever see anything about chance and stuff like that with confidence intervals, that's automatically wrong. Just like when we talk about hypothesis testing. Oh, we accept the null, blah, blah, blah. Confidence intervals, we're always talking about being a certain degree of confidence. So that tells us that A and B are our answers. So the researcher is 90% confident the applicants who use a professional resume writing service are approximately 5% to 17% more likely to be hired than those who did not. Yes. And those 5 and 17% are, if you notice, are limits from our confidence interval. So, can we conclude that a higher proportion of applicants get hired because they use a professional resume writing service? Why are we not? No, we cannot make this conclusion because this is an observational study that does not warrant a cause and effect conclusion. No, we can't make a conclusion because the confidence interval contains negative values. Well, that's not true. Yes, we can make this conclusion because the confidence interval contains only positive values. Yes, we can make this conclusion because this was an experiment that warrants a cause and effect conclusion. Did they randomly assign people to these? 500 total applicants across 20. Okay, it's not an experiment. So, as an experiment, we randomly assign people to the, to not being in the resume or the professional writing group. So, I'm going to say first that there appears to be a difference. Yes, because it contains only positive values. But what my gut was saying that it's going to be no, because it actually was a observational study, and that from observational studies we actually can't generalize cause and effect because it's not an experiment, because we did not randomly assign those treatments. So be careful of this. Observational studies do not warrant a cause and effect conclusion. Alright, well, I hope this helps. And if you have any questions, always email us. We are here to help you, and good luck on the test. See you guys.